Hi, my name is Catalin and together with my colleague Nilu, we are going to present our paper, Self-Supervised Predictive Convolutional Attentive Block for Anomaly Detection. This is joint work with our awesome supervisors, Radu, Kamal, Fahad, Professor Moslund and Professor Shah. The existing anomaly detection methods can be clustered into several categories, such as dictionary learning methods, change detection frameworks, and so on. Lately, there are many contributions in the area of reconstruction-based methods, which push the scores to new state-of-the-art levels. We focus on the latter direction, introducing a novel self-supervised predictive convolutional attentive block, for short SSPCAB. We are the first to introduce the reconstruction-based functionality as a basic building block for neural architectures. Our block is very general and easily pluggable into diverse architectures. Thus, we integrate our block into several state-of-the-art methods for anomaly detection, obtaining significant performance improvements across multiple datasets. Let's have a deep dive into our mask convolution approach. In the image is represented the receptive field of the proposed kernel. We only activate the corner regions denoted by subkernels K1 to K4. We consider the center of the kernel as a mask region which is not seen by our layer. In this manner, we build our mask convolution. The hyperparameters are d, the distance from the active subkernels K1 to K4 to the mask region, and K', the spatial support of the subkernels K. Now, let's see how our block is built. We have the mask convolution which can be placed at any layer or any stage into a network. The output of the mask convolution is processed by a channel attention module which computes an attention score for each channel. We devise a self-supervised task consisting of reconstructing the mask region inside our convolutional receptive field for every location where the mask filters are applied. To this end, our block should learn to provide the corresponding reconstructions as the output. We define the self-supervised reconstruction loss as the mean square error between the input and the output as depicted in the first equation. When integrated SSPCAB into a neural model, which has its own loss function LF, our loss can simply be added to the respective loss, resulting in a new loss function that comprises both of them.
We have two configurable parameters, dilation rate D and kernel size K'. We perform experiments on Avenue with an autoencoder based on SSPCAB using different kernel size and dilation rates. We obtain optimal results for D equal to 1 and K' equal to 1. We also perform experiment by adding channel attention, spatial attention, and both. Channel attention with a reduction rate R equal to 8 gives the best results. We use this configuration across our remaining experiments. We choose two baseline methods for image anomaly detection on MVTech AD, namely DREAM and cut-paste. These are the localization results after integrating our block into DREAM. The overall results are marked in blue. We have a significant improvement of 1.5% in terms of average precision. Considering the overall detection score, both DREAM and cut-paste show improvement after including our block. These are some qualitative results on MVTech AD, where red represents the ground truth, blue the baseline, green the model with SSPCAB. We observe significant improvement in terms of localization. The graph shows the performance of 4 baseline state-of-the-art method on Avenue before and after adding SSPCAB. In general, we observe the SSPCAB brings significant improvements. For example, the RBDC for Liu et al. at CV21 grows by 21%. These graphs show the performance changes induced by SSPCAB on Shanghai Tech for the same methods. Again, we see consistent improvement after including SSPCAB. Here we present the result on particular videos before and after adding SSPCAB in blue and green respectively. The red region marks the ground truth abnormal frame. The anomalies in the left example are throwing a bag and walking in wrong direction, whereas in the right example the anomalies is a person walking with a trolley. Thank you for listening. Our code is publicly available on GitHub. For questions, see you at poster session 3.2.